Every star you've ever seen in the night sky is already gone. Not metaphorically, not poetically. The light reaching your eyes left those stars hundreds, thousands, millions of years ago. And in the time it took that light to cross the void, those stars have moved, changed, perhaps died entirely. You're not looking at the universe as it is. You're looking at the universe as it was. And the farther you look, the deeper into the past you see, until distance and time become the same thing. This isn't philosophy. This is the fundamental nature of observation itself. If this interests you, consider subscribing. What follows will change how you understand everything you see. The James Webb Space Telescope has forced us to confront something unsettling. When it turned its instruments toward regions of space that appeared empty, voids where previous telescopes detected nothing but darkness, it found galaxies. Not just a few, thousands. Galaxies so distant that their light has been traveling toward us for more than 13 billion years. Galaxies that formed when the universe itself was barely a fraction of its current age. And these galaxies aren't behaving the way our models predicted they should. They're too bright, too massive, too structured, too mature. As if the early universe was fundamentally different than we thought, or as if our understanding of how cosmic structure forms is incomplete in ways we're only beginning to recognize. But before we can understand why these observations matter, we need to understand what we're actually looking at when we look into space. Because the universe doesn't work the way our everyday experience suggests it should. Stand outside on a clear night, far from city lights, and look up. The stars appear fixed, permanent, eternal. They seem to exist in the present moment, sharing the same now that you occupy. This is an illusion, a deeply ingrained one, built into how our brains process visual information. When you see an object in your immediate environment, a tree, a building, another person, the light from that object reaches your eyes almost instantaneously. The delay is measured in nanoseconds, billionths of a second, far too brief for your conscious mind to register. So your brain assumes that what you see is what exists right now, in this moment. But light doesn't travel instantaneously. It moves at a specific speed, roughly 300 million meters per second. In human terms, that's extraordinarily fast. In cosmic terms, it's agonizingly slow. Light from the sun takes about 8 minutes to reach Earth. That means when you look at the sun, though you shouldn't look directly at it, you're seeing it as it was 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd continue seeing it, receiving its light and warmth, completely unaware that the source of that light no longer existed. 8 minutes is trivial. The nearest star beyond our sun, Proxima Centauri, is about 4 light years away. The light you see from that star left its surface 4 years ago. You're seeing Proxima Centauri as it was 4 years in the past. Most of the stars visible to the naked eye are dozens, hundreds, or thousands of light years away. Betelgeuse, the red supergiant marking Orion's shoulder, is roughly 550 light years distant. The light from Betelgeuse that enters your eye tonight began its journey during the Renaissance, when Leonardo da Vinci was alive, when the printing press was still a recent invention, when the Americas were unknown to European cartographers. And those are the nearby stars, the ones in our immediate cosmic neighborhood. Our galaxy, the Milky Way, is approximately 100,000 light years across. Light from stars on the opposite side of the galaxy takes 100,000 years to reach us. We see them not as they are, but as they were 100,000 years ago, during the last ice age, when Homo sapiens were just beginning to migrate out of Africa, when Neanderthals still walked the Earth. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light years away. The light from Andromeda that reaches us tonight left that galaxy 2.5 million years ago, when early human ancestors were using the first stone tools, when the genus Homo was just emerging on the African savanna. You're not seeing Andromeda as it is now. You're seeing its ancient past, preserved in light, delivered across an almost incomprehensible gulf of space and time. This is what astronomers mean when they say distance in space is also distance in time. The farther away something is, the longer its light takes to reach us, and therefore the farther back in time we're seeing. This isn't a limitation of our instruments. It's not something better technology can overcome. It's built into the fabric of reality itself. Information cannot travel faster than light. Therefore, all observation is observation of the past. When astronomers look at distant galaxies, they're not just measuring how far away those galaxies are, they're measuring how long ago the light we're seeing left those galaxies. They're looking backward through time, and the James Webb Space Telescope, with its unprecedented sensitivity to infrared light, can look farther back than any telescope before it. It can see galaxies whose light has been traveling for more than 13 billion years. Galaxies that formed when the universe was less than 5% of its current age. Galaxies that existed when the cosmos was still emerging from its primordial state. But there's a complication. The universe isn't static, it's expanding. And this expansion changes everything. In the early 20th century, astronomers noticed something strange. When they examined the light from distant galaxies, they found that spectral lines, distinctive patterns created by specific elements absorbing or emitting light at characteristic wavelengths, were shifted toward the red end of the spectrum. This redshift, as it came to be called, was universal. Nearly every galaxy showed it, and the more distant the galaxy, the greater the redshift. There were different possible explanations for this observation. Perhaps the galaxies were moving away from us, and the motion was stretching the light waves, increasing their wavelength and shifting them toward the red. This would be similar to the Doppler effect you hear when an ambulance passes you on the street. The pitch of the siren drops as the vehicle moves away because the sound waves are stretched out by the motion. Or perhaps something else was happening, some property of space itself that affected light over vast distances. The astronomer Edwin Hubble, working with Milton Humason at the Mount Wilson Observatory, gathered more data. They measured the redshifts of numerous galaxies and compared them to estimates of those galaxies' distances. What they found was a clear relationship. The farther away a galaxy was, the greater its redshift. And the relationship was linear. Double the distance, double the redshift. This suggested that the universe itself was expanding, that space was growing, carrying galaxies away from each other, and that this expansion was stretching light waves as they traveled through space. This was a revolutionary idea. For most of human history, the cosmos was assumed to be eternal and unchanging. The heavens were fixed. The universe had always existed in essentially its current form and would continue to exist that way indefinitely. But if space was expanding now, that meant it was smaller in the past. Trace that expansion backward, and you arrive at a moment when all space, all matter, all energy was compressed into an infinitesimally small point. The universe had a beginning, a moment of origin, what we now call the Big Bang. The expansion of space has profound implications for how we observe the universe. As space expands, the light traveling through it gets stretched. The wavelength increases. Light that was emitted as visible light can be stretched into infrared. Light that was emitted as ultraviolet can be stretched into visible wavelengths. The farther the light travels, the more it gets stretched, and the more redshifted it becomes. This is why observing the early universe is so difficult. Galaxies that formed when the universe was young emitted light in the visible and ultraviolet range, just like galaxies do today. But that light has been traveling for billions of years, and space has been expanding the entire time. By the time that ancient light reaches us, it's been stretched so much that it's no longer visible light. It's infrared, sometimes far infrared. To see the earliest galaxies, you need a telescope that can detect infrared light with extreme sensitivity. The Hubble Space Telescope, for all its revolutionary discoveries, was primarily designed to observe visible and ultraviolet light. It could detect some near-infrared, but its capabilities in that range were limited. This meant there was a wall beyond which Hubble couldn't see clearly. Galaxies beyond a certain distance, beyond a certain point in cosmic history, faded into obscurity, not because they weren't there, but because their light had been redshifted beyond Hubble's ability to detect it. The James Webb Space Telescope was designed specifically to overcome this limitation. Its instruments are optimized for infrared observation. Its mirror is coated with gold, which reflects infrared light exceptionally well. Its detectors are cooled to temperatures barely above absolute zero, minimizing thermal noise that would otherwise interfere with detecting faint infrared signals. And it operates far from Earth, at a gravitationally stable point called L2, where there's no atmospheric interference and no thermal radiation from the planet itself. When Webb became operational and began its scientific observations, Astronomers pointed it at regions of sky that had been studied extensively by Hubble. One of these was the Hubble Ultra Deep Field, a tiny patch of apparently empty space that Hubble had observed for hundreds of hours, accumulating enough light to reveal the faintest, most distant galaxies ever seen at that time. When Hubble looked at this region, it found about 10,000 galaxies, many of them extremely distant and faint. When Webb looked at the same region, it found more, many more, galaxies that Hubble couldn't see, galaxies so distant and so redshifted that they were completely invisible to Hubble's instruments. And these weren't just a few additional galaxies filling in gaps. These were galaxies from the early universe, from an era that had been largely hidden from view. Galaxies that formed when the cosmos was between 200 million and 500 million years old, during what's called the epoch of reionization, when the first stars were ionizing the neutral hydrogen that filled space, transforming the universe from opaque to transparent. But the images were just the beginning. When astronomers analyzed the data, measuring the properties of these early galaxies, their brightness, their size, their structure, they found something unexpected. These galaxies were more luminous than they should have been, more massive, more developed. According to the prevailing models of galaxy formation, galaxies in the early universe should have been small, dim, irregular collections of stars, still in the process of assembling themselves through the gradual accumulation of matter. They should have been the building blocks that would eventually merge to form the large, structured galaxies we see in the later universe. Instead, what Webb revealed were galaxies that looked surprisingly mature. Some had already formed spiral structures. Some showed evidence of supermassive black holes at their centers, black holes that would have required hundreds of millions of years to grow to their observed masses. Some were so bright that they appeared to contain hundreds of millions or even billions of stars. All of this in a universe that was less than 500 million years old. This shouldn't have been possible. Not according to the standard timeline of cosmic evolution. The early universe, according to our models, was a hot, dense soup of particles. Protons, neutrons, electrons, photons, all in a state of thermal equilibrium. As space expanded, this primordial plasma cooled. About 380,000 years after the Big Bang, it cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. This moment, called recombination, is when the universe became transparent. Before recombination, photons couldn't travel far without scattering off free electrons. After recombination, they could travel unimpeded. The light released at this moment is what we now detect as the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. But after recombination, the universe entered what's called the Dark Ages. There were no stars yet, no galaxies, just clouds of neutral hydrogen, extremely diffuse, spread throughout expanding space. These clouds weren't perfectly uniform. There were tiny variations in density, quantum fluctuations that had been stretched to cosmic scales during an earlier period of extremely rapid expansion called inflation. Regions that were slightly denser than average had slightly stronger gravity. They pulled more matter toward themselves, and gravity is self-reinforcing. The more matter accumulates, the stronger the gravitational pull, the faster more matter accumulates. Over time, these density fluctuations grew. The denser regions became denser still, while the less dense regions became voids. The universe developed structure, but this process takes time. Gravity works slowly, especially when the matter involved is diffuse gas spread across vast distances. According to simulations, the first stars should have formed around 100 to 200 million years after the Big Bang. These would have been massive stars, hundreds of times the mass of our Sun, formed from pristine hydrogen and helium with no heavier elements yet present. They would have burned hot and bright, but lived short lives, perhaps only a few million years before exploding as supernovae and seeding the surrounding space with the first heavy elements. The first galaxies, small and irregular, should have assembled from multiple clusters of these early stars, drawn together by gravity. Over hundreds of millions of years, these protogalaxies would have merged, grown, formed structures, developed into the familiar spiral and elliptical galaxies we see in the later universe. This process, called hierarchical assembly, is the foundation of our understanding of how cosmic structure forms. But the galaxies Webb is finding don't fit this timeline. They're too advanced, too organized, too massive. Some appear to have already gone through multiple generations of star formation with older, redder stars coexisting alongside younger, bluer ones. Some show chemical compositions that indicate significant enrichment with elements heavier than hydrogen and helium, which requires many cycles of stellar birth, life, and death, all within the first few 100 million years of cosmic history. There are several possible explanations. Perhaps star formation in the early universe was far more efficient than we thought. Perhaps the first stars were more massive, burned brighter, and produced more heavy elements per generation than our models predict. Perhaps dark matter, the invisible substance that makes up most of the matter in the universe, clumped together faster than we expected, creating deeper gravitational wells that could accumulate ordinary matter more rapidly. Or perhaps our models are missing something fundamental. Perhaps the conditions in the early universe were different in ways we haven't accounted for. Perhaps there are physical processes we don't yet understand that accelerated the formation of structure during that first 500 million years. This is the scientific frontier that Webb has opened, not by answering questions, but by revealing that some of our answers were wrong, or at least incomplete. The early universe was not the simple, gradual, slow-building story we thought it was. It was chaotic, dynamic, rapid, violent. Galaxies assembled faster than they should have. Black holes grew larger than our models allow. Structure emerged from apparent chaos on timescales that challenge our understanding. And all of this is happening at distances so vast that the human mind struggles to comprehend them. When we say a galaxy is 13 billion light years away, what does that actually mean? It means the light we're seeing left the galaxy 13 billion years ago. But because space has been expanding during all that time, the galaxy itself is no longer where it was when the light was emitted. Space has stretched. The galaxy has been carried along with that expansion. By now, accounting for expansion, that galaxy is actually more than 30 billion light years away from us. We're seeing it where it was, not where it is. This creates a strange situation. The farther we look, the deeper into the past we see, until we reach a limit. Not a limit of space, but a limit of time. The universe has a finite age, about 13.8 billion years. Light that was emitted more than 13.8 billion years ago hasn't had time to reach us yet. Not because space is finite, but because time is. There's a horizon beyond which we cannot see, not because there's nothing there, but because the light from those regions hasn't had time to complete its journey across the expanding cosmos. This horizon defines what astronomers call the observable universe. It's a sphere centered on us with a radius of about 6.5 billion light years, accounting for the expansion of space during the time light has been traveling. Everything within this sphere is, in principle, observable. Everything beyond it is not. Not yet, perhaps not ever. But here's the critical point. The observable universe is not the universe. It's just the portion of the universe from which light has had time to reach us since the Big Bang. The total universe is almost certainly much larger. How much larger, we don't know. It could be a bit larger. It could be infinitely larger. Our observations can't tell us. All we can observe is what's inside our horizon. And this horizon is not static. You might think that as time passes, more light from more distant regions would reach us, expanding our observable universe. And in a sense, that's true. Light that's currently just beyond our horizon will eventually cross that threshold and become visible. But there's a complication. Space is expanding, and not just expanding, accelerating. The rate of expansion is increasing over time. This acceleration, driven by something called dark energy that we don't understand, has a profound effect. Distant galaxies are being carried away from us by the expansion of space. The farther away they are, the faster they're receding. At some distance, they're receding faster than the speed of light. This doesn't violate relativity. Nothing is moving through space faster than light, but space itself can expand at any rate. And light emitted from those galaxies, even though it's traveling toward us at the speed of light, is losing ground. It's like running on a treadmill that's accelerating faster than you can run. You're moving forward, but you're still falling behind. There's a distance beyond which galaxies are receding so fast that light emitted from them now will never reach us. The expansion of space will outpace the light's progress. These galaxies are crossing what's called the cosmic event horizon. They're leaving our observable universe, not because they're being destroyed, but because the structure of space-time makes it impossible for information from them to ever reach us again. And this isn't just happening to a few distant galaxies. It's happening to most galaxies. The observable universe is shrinking in terms of the number of galaxies we can potentially observe. Galaxies that are currently visible will, over billions of years, fade, redshift into invisibility, and eventually cross the event horizon. Far in the future, assuming no catastrophic changes to the expansion rate, an observer looking into space will see fewer and fewer galaxies. Eventually, only the galaxies in our local gravitational group, the Milky Way, Andromeda, and a few dozen smaller companions, will remain visible. The rest of the universe will have been carried beyond the horizon, leaving only darkness. Think about what that means. The vast majority of the universe, the galaxies, the stars, the planets, the whatever else exists out there, is already inaccessible to us. We can see the light they emitted in the past, but we can never visit them, never send signals to them, never receive signals from them, never learn what happened to them after the moment when the light we're seeing left their vicinity. They exist in a region of space-time that is fundamentally disconnected from our own future. And that's just the observable universe, the portion we can theoretically see. The unobservable universe, the regions beyond our cosmic horizon, could be vastly larger. Some models suggest the total universe is hundreds of times larger than the observable portion. Some suggest it's infinite. We have no way to know. The information simply isn't accessible to us. This is a different kind of unknown than the unknown science has confronted before. When scientists in the 19th century didn't know what stars were made of, that was a problem that could be solved with better instruments and more data. When we didn't know how continents moved, that was a mystery that could be unraveled through observation and theory. But the unobservable universe is unobservable not because our instruments aren't good enough, but because of the fundamental structure of space-time. No improvement in technology will allow us to see beyond the cosmic event horizon. The information from those regions is causally disconnected from us. It's not that we don't know what's out there, it's that we cannot know. Not now, not ever. This raises uncomfortable questions about what we mean when we talk about understanding the universe. We can study the observable universe. We can measure its properties, track its evolution, build models that explain what we see. But the observable universe is just a sample, a tiny, perhaps infinitesimal, fraction of the total. And we have no way to verify that the sample is representative. We assume the laws of physics are the same everywhere. We assume the distribution of matter is roughly uniform on the larger scales. We assume the portion we can see is typical of the whole, but these are assumptions. We can't test them. The evidence is forever beyond our reach. The James Webb Space Telescope has expanded our view deeper into the past than ever before. It's revealing galaxies from cosmic epochs we've never clearly seen. It's challenging our models of how structure forms, forcing us to reconsider our assumptions about the early universe. But it's also making clear just how limited our view is. We're seeing farther, yes, but we're also confronting the limits of what can be seen. We're approaching the horizon beyond which observation becomes impossible. And even within the observable universe, what we can see is constrained by more than just distance. It's constrained by the nature of light itself. Light is our primary tool for observing the cosmos. Nearly everything we know about the universe comes from detecting and analyzing electromagnetic radiation, light in its various forms, from radio waves to gamma rays. But light only tells us about things that emit or reflect light. Stars, galaxies, nebulae, the hot gas between galaxies. These are visible because they're hot, or because they're illuminated by something else that's hot. But most of the matter in the universe doesn't emit light. It doesn't interact with electromagnetic radiation at all, except through gravity. We call it dark matter, not because it's literally dark, but because it's invisible. It doesn't absorb light. It doesn't emit light. It doesn't scatter light. It's completely transparent to every form of electromagnetic radiation we can detect. We know dark matter exists because we can see its gravitational effects. Galaxies rotate faster than they should based on the mass of visible matter alone. Clusters of galaxies hold together with more gravitational force than their visible stars and gas can provide. The paths of light bend around massive objects, in ways that require more mass than we can see. All of this points to the presence of enormous amounts of matter that we cannot observe directly. Current estimates suggest that dark matter makes up about 85% of all matter in the universe. The ordinary matter that makes up stars, planets, gas, dust, and everything we can see accounts for only about 15%. We're living in a universe composed mostly of something we don't understand, can't see, and can only infer from its gravitational influence. And then there's dark energy, which is even more mysterious. While dark matter at least behaves like matter, it clumps together, forms structures, pulls on other matter through gravity. Dark energy is something else entirely. It behaves like a property of space itself. It doesn't clump, it's uniform, and its effect is to push space apart, driving the accelerating expansion of the universe. We know almost nothing about what dark energy actually is. It could be a cosmological constant, an inherent energy density of space itself. It could be a dynamic field, something that varies over time or space. It could be a sign that our understanding of gravity is incomplete, that general relativity needs modification on cosmic scales. We don't know. What we do know is that it makes up about 68% of the total energy content of the universe. Add it all up, and the picture is humbling. Ordinary matter, the stuff we're made of, the stuff that makes up stars and planets, and everything we can see, accounts for less than 5% of the universe. Dark matter accounts for about 27%. Dark energy accounts for about 68%. 95% of the universe is composed of things we don't understand, and these aren't minor details. They're the dominant components. When we look at the universe, we're seeing a thin frosting of ordinary matter on top of a vast, invisible substrate of dark matter and dark energy. We're observing the visible tip of an iceberg, with no way to directly examine the bulk that lies hidden beneath. The James Webb Space Telescope, for all its power, can only observe the ordinary matter. It can't see dark matter. It can't see dark energy. It can see the effects of these things, how dark matter shapes the distribution of galaxies, how dark energy drives cosmic expansion, but the substances themselves remain invisible, detectable only through their gravitational influence. This is a profound limitation. Imagine trying to understand an ocean ecosystem by only observing the few creatures that break the surface. You'd see whales breaching, seabirds diving, the occasional fish leaping, but you'd miss the vast complexity beneath the waves, the schools of fish, the coral reefs, the deep sea creatures, the currents and temperature gradients that shape the entire system. Your understanding would be fundamentally incomplete, not because you weren't observing carefully enough, but because most of what matters is hidden from view. That's our situation with the universe. We're surface observers, watching the small fraction of cosmic reality that happens to interact with light, while the vast majority of what exists operates invisibly, shaping and influencing the visible matter in ways we can only partially infer. And there's another layer of limitation we haven't discussed yet. Even the light we can detect only tells us about the past. It carries no information about what's happening now in the distant regions we're observing. That information is on its way, traveling at the speed of light, but it won't arrive for millions or billions of years. We have no way to know the present state of distant galaxies. We can only see their history. This creates a strange disconnect between the universe as it is and the universe as we observe it. When you look at a galaxy a billion light years away, you're seeing it as it was a billion years ago. That galaxy, at this very moment, is in some state we cannot observe. It might have collided with another galaxy. It might have formed new stars or lost old ones. Its central black hole might have consumed more matter and grown, or it might be essentially unchanged. We have no way to know. The information about its current state exists, but it's not accessible to us yet. It won't be accessible for a billion years. In a sense, we live in a universe of ghosts. Every star, every galaxy, every distant object we observe is a ghost of something that existed in the past. The present state of those objects is hidden from us, replaced by an image from history, preserved in light, delivered across the void. And the farther we look, the older the ghosts become. The galaxy's web is observing near the edge of the visible universe are ghosts from more than 13 billion years ago. We're seeing them as they were when the universe was young, when the first structures were forming, when cosmic evolution was just beginning. Those galaxies today, if we could somehow observe them as they are now, would be vastly different. They've had more than 13 billion years to evolve, to merge with other galaxies, to form new stars, to develop complex structures. But we can't see that evolution. We can only see the beginning. There's a thought experiment sometimes posed to illustrate this strange relationship between observation and reality. Imagine an extremely advanced civilization in a galaxy 10 billion light years away. Imagine they have a telescope powerful enough to resolve details on Earth's surface. What would they see if they pointed that telescope at our planet? They wouldn't see cities. They wouldn't see humans. They wouldn't see civilization. They'd see Earth as it was 10 billion years ago, long before life as we know it existed. They'd see a planet in the early stages of its history, perhaps still being bombarded by asteroids, perhaps with a very different atmosphere and surface. The information about present-day Earth exists, but it's in transit, traveling through space at the speed of light, and it won't reach that distant civilization for another 10 billion years. Similarly, when we observe distant galaxies, we're seeing their ancient past. Those galaxies have continued evolving, but their present state is inaccessible to us. We're separated not just by space, but by time. And as the universe continues to expand, as more galaxies cross the cosmic event horizon, larger and larger portions of cosmic reality will become forever inaccessible, their present states hidden behind an expanding wall of space-time. This is what makes the scale of the universe not just large, but terrifying. It's not merely that space is vast, it's that the vastness imposes fundamental limits on what we can know. Most of the universe is invisible to us, composed of dark matter and dark energy we don't understand. Most of the observable universe shows us only the past, with the present hidden behind the speed of light delay. And most of the total universe is beyond our cosmic horizon, causally disconnected. Its very existence unprovable from our perspective. We're living in a universe that is vastly larger, vastly older, and vastly more complex than our everyday experience suggests. And we're confined to observing a tiny, unrepresentative sample of it, seeing only the ordinary matter, only the past, only the portion close enough that light has had time to reach us. The discoveries Webb is making, the early galaxies, the unexpected maturity of cosmic structure in the young universe, the challenges to our models are important. They're advancing our understanding, they're revealing new mysteries, but they're also making clear just how much we don't know. Every answer raises new questions. Every observation reveals new complexity. Consider what it means to observe a galaxy from 13 billion years ago. The light entering Webb's instruments left that galaxy when the universe was barely 5% of its current age. It's been traveling through expanding space ever since, gradually redshifting as the wavelengths stretched, carrying information about conditions in the early cosmos. That light has crossed more than 99% of the observable universe to reach us. And what does it tell us? It tells us that galaxy existed. It tells us roughly how massive it was, how bright, what elements it contained, how fast it was forming stars. But it doesn't tell us why. It doesn't tell us how it assembled so quickly. It doesn't tell us what happened to it afterward. That galaxy, if it still exists in some form, is now far beyond our reach, carried away by cosmic expansion. We can never visit it. We can never communicate with it. We can only observe the ancient light it emitted billions of years ago and try to piece together a story from that fragmentary evidence. This is the nature of cosmology. We're archaeologists sifting through ancient light, trying to reconstruct the history of the universe from scattered remnants. And unlike terrestrial archaeology, where you can sometimes find new sites or dig deeper in existing ones, cosmology has hard limits. The evidence that exists is all the evidence we'll ever have. The light from the early universe has already reached us, or is on its way. There will be no more. The cosmic event horizon is closing, not opening. The universe we can observe is shrinking in terms of accessible information, not expanding. Future astronomers, thousands or millions of years from now, assuming humanity or its descendants still exist, will have access to less cosmic information than we do. More galaxies will have crossed the event horizon. The cosmic microwave background, the afterglow of the Big Bang, will have redshifted further, becoming harder to detect. The evidence of the universe's origin and early evolution will have faded. Those future observers might look into the sky and see only the local cluster of galaxies, surrounded by darkness. with little indication that a vast cosmos once existed beyond. There's a certain irony in this. We live at a time when the universe is still revealing its secrets, when the evidence of cosmic history is still accessible, when we can look back billions of years and see the early stages of structure formation. We're living in a cosmological golden age, but it's a fleeting one. The window is closing, not in our lifetimes, or in the lifetimes of our distant descendants, but on cosmic timescales. The era when the full history of the universe is observable is already passing. And even now, in this golden age, we're missing most of the story. We can see galaxies forming, but we can't see the dark matter halos they formed within. We can measure cosmic expansion, but we don't know what dark energy is or why it exists. We can detect the cosmic microwave background, but we can't observe the moments before it was emitted, the first fraction of a second after the Big Bang, when the universe was so hot and dense that no light could escape. There are limits to observation that go beyond distance and time. There are limits imposed by the physics of the early universe. In the first 380,000 years after the Big Bang, the universe was opaque. Photons couldn't travel freely. They scattered constantly off free electrons, trapped in the hot plasma. This means we can't use light to observe the universe before recombination. There's a wall, the surface of last scattering, beyond which the universe is invisible to electromagnetic observation. Scientists have proposed other ways to observe the pre-recombination universe. Gravitational waves, ripples in space-time itself, could carry information from those earliest moments. Unlike light, gravitational waves wouldn't have been blocked by the opaque plasma. They would have traveled freely, carrying information about cosmic conditions shortly after the Big Bang. But detecting primordial gravitational waves is extraordinarily difficult. The signals are weak, and they're buried under noise from more recent sources. So far, we haven't detected them. Neutrinos, nearly massless particles that barely interact with matter, could also carry information from the early universe. There should be a cosmic neutrino background, analogous to the cosmic microwave background, but composed of neutrinos rather than photons. These neutrinos decoupled from matter about 1 second after the Big Bang, earlier than photons, and have been traveling freely ever since. Detecting them would give us a window into even earlier cosmic conditions. But neutrinos are notoriously difficult to detect. They pass through ordinary matter as if it isn't there. Building a detector sensitive enough to catch the faint signals from the cosmic neutrino background is beyond current technology. So we're left with light, and light can only show us the universe from 380,000 years after the Big Bang onward. The earlier moments, the first seconds, the first minutes, the first thousands of years, are hidden behind a wall of opacity. We can infer what happened during that time based on our understanding of physics, based on the conditions we observe later, based on theoretical models. But we can't directly observe it. This is another fundamental limit. Even if we built a telescope 1,000,000 times more powerful than Webb, even if we could detect every photon that exists, we still couldn't see the universe before recombination. The information isn't there. The light that would carry that information was trapped, absorbed, scattered, erased before it could escape. The universe is structured in a way that hides its deepest secrets. The very early moments are obscured by opacity. The very distant regions are obscured by cosmic expansion and the speed of light limit. The vast majority of matter and energy is dark, invisible to our instruments, and the present state of distant objects is hidden behind light travel time. We're observers in a cosmos that seems almost designed to frustrate observation. Every layer of mystery we peel back reveals another layer beneath. Every question we answer raises new questions. Every limit we approach reveals another limit beyond it. And yet, we continue observing. We build better telescopes. We develop more sophisticated theories. We push the boundaries of what's knowable, even as we become more aware of how much will never be known. The James Webb Space Telescope represents the current frontier of this endeavor. It's showing us galaxies we've never seen before, from an era of cosmic history that was previously obscure. It's revealing that the early universe was more complex, more dynamic, more structured than we expected, and it's forcing us to confront uncomfortable truths about the limits of our knowledge. Those early galaxies Webb is observing, the ones that are too bright, too massive, too mature for their age. What are we actually seeing? We're seeing light that's been traveling for over 13 billion years. We're seeing structures that formed in the first few 100 million years of cosmic history. We're seeing a universe that doesn't quite match our models, but we're not seeing those galaxies as they are now. We're seeing them as they were then. And no is a problematic concept when discussing objects billions of light years away. There's no universal now. Relativity tells us that simultaneity is relative, that observers in different reference frames will disagree about what events are happening at the same time. When we talk about what a distant galaxy is doing, we have to specify a reference frame. And even in our reference frame, the information about that galaxy's current state doesn't exist here yet. It's in transit, traveling at the speed of light, and won't arrive for billions of years. This creates a strange fragmentation of cosmic reality. The universe exists in multiple temporal states simultaneously, depending on your perspective. From our point of view, distant galaxies exist in the past. From their point of view, assuming there are observers there, we exist in the past. If we could somehow send a signal to a galaxy 10 billion light years away, and they could somehow send a signal back, the round-trip communication would take 20 billion years. By the time we received their response, assuming both civilizations survived that long, the question we asked would have been sent by ancestors who lived longer ago than recorded human history. This is the tyranny of distance in an expanding universe. Not only is most of reality inaccessible, but even the accessible portion is fragmented across time, with different regions existing in different temporal states from our perspective. The universe doesn't have a single, coherent present. It has a fragmented, light, limited present that varies depending on where you are and what you can observe. And as cosmic expansion continues, as dark energy drives the acceleration of that expansion, the fragmentation will increase. More galaxies will cross the event horizon. More information will become inaccessible. The observable universe will contract, not in space, but in information content. Future observers will have access to less cosmic history, fewer galaxies, less evidence of what the universe once was. There's a concept in cosmology called the Big Rip, a hypothetical scenario for the ultimate fate of the universe if dark energy continues to increase in strength. In this scenario, the expansion of space accelerates faster and faster, until it overcomes not just the gravitational binding of galaxy clusters and galaxies, but eventually the gravitational and electromagnetic forces holding smaller structures together. First, galaxy clusters would be torn apart, then galaxies, then stellar systems, then stars themselves, then planets, then molecules, then atoms. Eventually, even subatomic particles would be ripped apart by the expansion of space. This is probably not the actual fate of the universe. Current observations suggest dark energy is a cosmological constant, which would drive eternal exponential expansion, but wouldn't tear apart bound structures. But the Big Rip scenario illustrates something important about the relationship between expansion and structure. Expansion is a destructive force, in a sense. It works against gravity, against the tendency of matter to clump together, against the formation of stable structures. The fact that we have galaxies, stars, planets, and life at all is because gravity, in certain regions, was strong enough to overcome expansion and pull matter together before it could be carried away. But that victory is temporary and local. On the largest scales, expansion wins. Galaxy clusters are the largest gravitationally bound structures in the universe. Anything larger, superclusters, cosmic filaments, the large-scale structure itself, is not bound. It's being pulled apart by expansion. And even within bound structures like galaxies, expansion is always present, always working to drive things apart, held in check only by the strength of gravity. In the very long term, assuming expansion continues, even bound structures will face a kind of cosmic isolation. The Milky Way and Andromeda will likely merge into a single large galaxy. The local group of galaxies, held together by mutual gravity, will eventually coalesce into one massive structure. But everything else, all the other galaxies, all the other groups and clusters, will be carried away beyond the cosmic event horizon. Our merged galaxy will exist in an island universe, surrounded by expanding darkness, with no visible evidence that a larger cosmos once existed. Observers in that far future, looking into the sky, would see stars, but no other galaxies. They would have no cosmic microwave background to detect, or it would be so redshifted as to be undetectable. They would have no evidence of the Big Bang. They would have no reason to think the universe had a beginning. Their cosmology would be fundamentally different from ours, and it would be wrong, but they would have no way to know it. All the evidence would be gone, carried away by expansion, redshifted into invisibility. This raises a disturbing question. Are we in a similar position? Is there evidence of cosmic history or cosmic structure that's already been carried beyond our horizon, already been redshifted into undetectability? Are there features of the universe that earlier observers could have seen, but that we can no longer detect? Have we already lost information that would change our understanding of cosmology? We have no way to know. If information has been lost, we have no record of what it was. We can only observe what's still observable, and we have to construct our cosmology based on that limited sample, hoping it's representative, but unable to verify that hope. The early galaxies Webb is observing might be giving us hints of what we're missing. Their unexpected properties, their brightness, their mass, their structure, suggest that something happened in the early universe that our models don't capture. Perhaps star formation was more efficient. Perhaps the initial density fluctuations were larger. Perhaps dark matter behaved differently. Or perhaps there's a piece of physics we haven't discovered yet, something that was important in the early universe, but isn't obvious in the later, more evolved cosmos. One possibility that's been suggested is that the initial mass function of stars, the distribution of stellar masses when stars form, was different in the early universe. Today, when a cloud of gas collapses to form stars, most of the stars that form are small dim red dwarfs. Massive stars are rare, but massive stars are much brighter than small stars. A star 10 times the mass of the Sun can be thousands of times brighter. A star 100 times the mass of the Sun can be millions of times brighter. If the early universe preferentially formed massive stars, that would explain why early galaxies are so bright. A population of massive stars would produce far more light per unit mass than a population dominated by red dwarfs, and massive stars burn through their fuel quickly, living only a few million years before exploding as supernovae. Those explosions would produce and distribute heavy elements, enriching the gas and allowing subsequent generations of stars to form with different compositions. This would also explain why early galaxies show evidence of chemical enrichment. If the first stars were massive, they would have lived, died, and seeded the interstellar medium with heavy elements very quickly, within a few tens of millions of years. Subsequent star formation would incorporate those elements, producing stars with compositions more like what we see in later galaxies. But this is still speculative. We don't know why the initial mass function would be different in the early universe. We don't have direct observations of those first massive stars. They existed before the galaxy's Webb is observing, and their light has long since faded. We can only infer their existence from the properties of the galaxies that came after. Another possibility is that supermassive black holes grew faster than we thought possible. Many of the early galaxies Webb has observed show signs of active galactic nuclei, extremely bright regions at the galaxy's center powered by matter falling into a supermassive black hole. These black holes, in galaxies less than 500 million years old, can have masses of hundreds of millions, or even billions of times the mass of the Sun. Standard black hole growth models suggest this shouldn't be possible. A black hole grows by accreting matter, but there's a limit to how fast accretion can occur, called the Eddington limit, determined by the balance between the gravitational force pulling matter in and the radiation pressure from the energy released as matter falls in. Above the Eddington limit, radiation pressure blows matter away, preventing further accretion. If black holes grew at the Eddington limit continuously from the earliest possible seed black holes, perhaps black holes formed from the first generation of massive stars with masses of tens or hundreds of solar masses. They could reach a few million solar masses by the time the universe was a few hundred million years old. But the black holes Webb is observing are much more massive than that, hundreds of millions of solar masses, in some cases approaching a billion. For these black holes to exist, they either had to start from much larger seeds, perhaps 100, 1,000 or million solar mass black holes that formed directly from collapsing gas clouds in the early universe, or they had to accrete faster than the Eddington limit allows. Both possibilities challenge our understanding. direct collapse black holes are theoretically possible, but require specific conditions. Clouds of pristine hydrogen that avoid fragmenting into stars, which is difficult to achieve. And super Eddington accretion requires conditions that aren't well understood. Yet the black holes exist. We can see them, or at least we can see the light from the matter falling into them. They're real, which means something about our models is wrong or incomplete. This is a pattern in modern cosmology. We observe things that shouldn't exist according to our models. Early galaxies that are too mature, black holes that are too massive, cosmic structures that are too large for the time available to form them. And each of these observations forces us to revise our understanding, to add complexity to our models, to acknowledge that the universe is more intricate than we thought. But there's a deeper issue here. All of our models are based on the assumption that the laws of physics are the same everywhere and at all times. We assume that gravity worked the same way in the early universe as it does now. We assume that the electromagnetic force, the strong and weak nuclear forces, the properties of matter and energy, all of these were the same 13 billion years ago as they are today. This is a reasonable assumption. It's the foundation of modern physics. The laws of nature are universal and unchanging, but it's an assumption. We can't verify it directly. We can't travel to the early universe and measure the strength of gravity or the speed of light. We can only observe the light from that era and interpret it using our current understanding of physics. If the laws of physics were different in the early universe, our interpretations would be wrong. The distances we calculate would be wrong. The masses would be wrong. The timescales would be wrong. Everything would be wrong in ways we couldn't detect because our entire framework for interpreting observations would be built on incorrect assumptions. This is unlikely. There are many consistency checks that suggest the laws of physics have been constant, at least in the observable universe, since shortly after the Big Bang. The cosmic microwave background, for instance, can be explained in exquisite detail using known physics. The abundances of light elements, hydrogen, helium, lithium, match the predictions of Big Bang nucleosynthesis, a model based on current physics applied to the early universe. The large-scale structure of the universe, the distribution of galaxies and voids, matches predictions from models that use general relativity and standard particle physics, but all likely is not the same as impossible. And the observations Webb is making, galaxies that challenge our models, structures that shouldn't exist, phenomena we can't fully explain, are reminders that our understanding is incomplete. We're working with a limited sample of data from a limited range of cosmic epochs, interpreted using theories that, while successful, are known to be incomplete. General relativity doesn't account for quantum mechanics. The standard model of particle physics doesn't include gravity. Neither explains dark matter or dark energy. We're trying to understand the entire universe using theories we know are provisional, approximations that work in the regimes we've tested, but might fail in regimes we haven't. And the early universe, with its extreme densities and temperatures, with its rapid evolution and exotic conditions, is precisely the kind of regime where our theories might break down. The more we observe, the more we realize how much we're assuming. Every calculation rests on layers of prior assumptions. We assume we understand the properties of light. We assume we understand how light interacts with matter. We assume we understand gravity. We assume we understand the expansion of space. Each assumption is based on tests and observations, but those tests have limits. We've never observed gravity in the conditions present in the first microsecond after the Big Bang. We've never measured the properties of matter at energies approaching the Planck scale. We're extrapolating, extending our theories beyond the regimes where they've been tested and hoping they still apply. Most of the time, this works. Our extrapolations make predictions, and observations confirm them. This gives us confidence that we're on the right track, but occasionally we encounter anomalies, observations that don't fit, phenomena that require new physics, or at least modifications to existing physics. Dark matter and dark energy are the most prominent examples. We know they exist because of their effects. Dark matter through its gravitational influence on visible matter, dark energy through its effect on cosmic expansion. But we don't know what they are. They're not accounted for in the standard model of particle physics. They're additions, things we've had to introduce to make our observations make sense. This is the situation we're in. We're observing a universe that's mostly composed of things we don't understand, seeing light from epochs we can't fully explain, trying to build a coherent picture from fragmentary evidence, and constantly encountering reminders that our picture is incomplete. And the scale compounds the difficulty. The universe is not just large, it's large in a way that makes investigation difficult. If you want to study biology, you can collect samples, perform experiments, test hypotheses. If you want to study geology, you can dig, drill, analyze rocks. If you want to study chemistry, you can mix substances, observe reactions, isolate variables. But you can't experiment on the universe. You can only observe. You can't rerun the Big Bang to see if you get the same result. You can't adjust the density of dark matter and watch how structure formation changes. You can't isolate a galaxy in a laboratory and study its evolution in controlled conditions. You have one universe, one history, one set of observations, and from that single example, you're trying to extract universal laws. This is an epistemological challenge unlike any other science faces. Most sciences can rely on repeated observations, controlled experiments, multiple examples. Cosmology has one example, one universe, one Big Bang, one cosmic history. We're trying to understand universal principles from a single case study, and it's not even a complete case study. We can't observe most of the universe. We can't observe most of cosmic history. We can't observe most of the matter and energy. We have a fragmentary, partial, incomplete view of a single example, and from that we're trying to infer how universes work. It's remarkable that we've made as much progress as we have. The standard model of cosmology, the lambda CDM model, which includes dark energy, lambda, and cold dark matter, CDM, explains a vast range of observations. The cosmic microwave background, the large-scale structure, the abundance of elements, the expansion history. It's a successful model, but it's also a model filled with unknowns. Dark matter is unknown. Dark energy is unknown. The initial conditions that led to the Big Bang are unknown. The ultimate fate of the universe is unknown. We've mapped out a history. The universe began in a hot, dense state, expanded and cooled, formed atoms, formed stars, formed galaxies, and continues expanding, driven by dark energy. This history is supported by evidence, but it's a sketch, not a detailed picture. We don't know why the Big Bang happened. We don't know what came before, or if before even makes sense. We don't know why the initial conditions were what they were. We don't know why the laws of physics are what they are. These are questions cosmology can't answer. They're beyond the reach of observation. We can trace cosmic history back to fractions of a second after the Big Bang, but not to the beginning itself. We can observe the effects of physical laws, but not their origin. We can map the universe, but not explain why there is a universe at all. The James Webb Space Telescope, despite its power, despite its ability to see farther and deeper than any instrument before it, is still operating within these fundamental limits. It can show us early galaxies, but it can't tell us why galaxies exist. It can measure cosmic expansion, but it can't explain dark energy. It can detect the signatures of supermassive black holes, but it can't reveal how they grew so large so quickly. What Webb is doing, really, is refining our sketch, adding details, correcting errors, revealing complexities we hadn't anticipated. But the fundamental limits remain. We're still observing only ordinary matter. We're still seeing only the past. We're still confined to the observable universe, and the scale of what we're missing is staggering. Think about dark matter. 85% of all matter is dark matter. It's invisible, but it's there, forming halos around galaxies, filling the space between galaxy clusters, shaping the large-scale structure of the universe through its gravity. Every galaxy is embedded in a dark matter halo that extends far beyond the visible stars. The Milky Way's dark matter halo might extend hundreds of thousands of light years from the galactic center, perhaps even more. The visible disk of the galaxy, the stars we see, is just a small component embedded in this much larger, invisible structure. Dark matter doesn't just sit there passively. It was crucial to galaxy formation. In the early universe, ordinary matter, hydrogen and helium gas, was spread fairly uniformly through space. But dark matter, which doesn't interact with radiation, could clump together before ordinary matter could. Dark matter formed the first structures, creating gravitational wells that attracted ordinary matter. When the ordinary matter fell into these wells, it heated up, radiated energy, and condensed into stars and galaxies. Without dark matter, galaxies as we know them might not exist. The ordinary matter wouldn't have clumped together quickly enough. The universe would look very different. Perhaps no galaxies, no stars, no planets, no life. Dark matter is foundational to cosmic structure, and we don't know what it is. We've searched for dark matter particles. We've built sensitive detectors deep underground, shielded from cosmic rays and background radiation, hoping to catch the rare interaction of a dark matter particle with ordinary matter. We've looked for evidence of dark matter particles annihilating or decaying, producing detectable radiation. We've searched for axions, YMPs, sterile neutrinos, and other hypothetical particles that could constitute dark matter. So far, we've found nothing. It's possible that dark matter doesn't interact with ordinary matter in any way except through gravity. If that's the case, we might never detect it directly. We'd be left inferring its existence and properties solely from its gravitational effects, 永远 unable to study it in a laboratory, unable to determine what it's made of. This is a sobering possibility. A fundamental component of the universe, making up most of its matter, might be forever beyond our ability to understand at a microscopic level. We could map its distribution, measure its density, observe its effects, but we might never know what it actually is. And dark energy is even more mysterious. At least with dark matter, we have a sense of how it behaves. It clumps together, it forms structures. It acts like matter, just invisible matter. Dark energy doesn't behave like anything familiar. It doesn't clump, it's uniform throughout space. It exerts negative pressure, driving cosmic expansion rather than resisting it. It seems to be a property of space itself, a background energy density that doesn't dilute as space expands. This is bizarre. Normally, when space expands, the density of matter and energy within it decreases. If you have a box of gas and you expand the box, the gas spreads out and its density drops. But dark energy doesn't work that way. As space expands, the dark energy density stays constant. More space means more dark energy. It's as if space itself has energy, and creating more space creates more energy. Where does this energy come from? It seems to violate conservation of energy, one of the most fundamental principles in physics. Energy can't be created or destroyed, only transformed. Yet dark energy appears to be created continuously as space expands. The resolution might be that energy conservation in general relativity is more subtle than in classical physics. In an expanding universe, energy isn't necessarily conserved globally. The expansion itself can create or destroy energy. But this is a technical point that doesn't really explain what dark energy is or where it comes from. Some physicists think dark energy is the cosmological constant, a term that Einstein introduced into his equations of general relativity and later regretted. The cosmological constant represents a baseline energy density of empty space, the vacuum itself. Quantum field theory predicts that the vacuum isn't truly empty, but filled with fluctuating quantum fields, and these fluctuations should contribute an energy density to space. If you calculate what that energy density should be based on quantum field theory, you get a number that's absurdly large, about 120 orders of magnitude larger than the observed dark energy density. This is sometimes called the worst prediction in physics. The theoretical vacuum energy is huge. The observed dark energy is tiny. They're related. Both are energy densities of empty space, but they differ by a factor of 10 to the 120th power. Something is cancelling out almost all of the vacuum energy, leaving just a tiny residual amount that we observe as dark energy. But we don't know what's doing the cancelling or why it's so precisely balanced. Other physicists think dark energy might not be constant, but could be a dynamic field, something that changes over time or varies from place to place. This would be called quintessence, and it would have different implications for the future of cosmic expansion. But there's no compelling evidence for quintessence over a simple cosmological constant, and no compelling theory for what such a field would be or how it would work. So dark energy remains a mystery. We know it exists. We can measure its effects. We can determine that it makes up about 68% of the universe's total energy density. But we don't know what it is, why it exists, or where it comes from. This is the state of cosmology in the early 21st century. We've mapped the history of the universe. We've measured its age, its expansion rate, its composition. We've observed galaxies forming and evolving over billions of years. We've detected the afterglow of the Big Bang. We've built a detailed, quantitative model of cosmic evolution. And yet, most of what the universe is made of remains unknown. The James Webb Space Telescope can't solve this problem. It can observe the ordinary matter, the 5% of the universe that emits or absorbs light. It can refine our measurements. It can reveal new details about galaxy formation, star formation, the chemical evolution of the cosmos. But it can't see dark matter. It can't detect dark energy directly. It operates within the same fundamental constraints that limit all electromagnetic observations. And even within those constraints, it's encountering mysteries. The early galaxies that are too bright, too massive, too mature. The supermassive black holes that grew too quickly. The structures that formed too early. These aren't just minor discrepancies. They're hints that something significant is missing from our understanding. Perhaps the models of star formation in the early universe need revision. Perhaps the initial mass function was different. Perhaps feedback processes, the ways that stars and black holes affect their surroundings through radiation, winds, and explosions, worked differently when the universe was young. Perhaps the dark matter distribution was clumpier than we thought. Perhaps there are aspects of galaxy formation physics that we haven't fully accounted for. Or perhaps something more fundamental is wrong. Perhaps general relativity needs modification. Perhaps the expansion history is different than we calculated. Perhaps the cosmic timeline itself is uncertain in ways we haven't recognized. These are not comfortable possibilities. Science progresses by building on established knowledge, refining theories, extending them into new domains. Overturning fundamental theories is rare and disruptive. It requires compelling evidence, not just anomalies. The anomalies Webb is finding might be explainable within the current framework, with adjustments and refinements, but they might not be. And if they're not, if they require more substantial revisions to our understanding, then much of what we thought we knew about the early universe might need to be reconsidered. This has happened before in the history of cosmology. In the early 20th century, the universe was thought to be static and eternal. Then observations of galactic redshifts revealed expansion, and the static eternal universe was replaced with the Big Bang model. In the late 20th century, cosmologists debated whether the expansion was slowing down as gravity pulled matter back together, or whether it would continue forever. Then observations of distant supernovae revealed that expansion is accelerating, driven by dark energy, and the decelerating universe was replaced with the accelerating universe. Each of these revolutions was driven by observations that didn't fit the prevailing model, and each revolution revealed that the universe was stranger, more complex, more mysterious than previously thought. The observations from Webb might be triggering another such revolution, or they might not. It's too early to tell. More data is needed, more analysis, more modeling, but the pattern is familiar. Observations reveal anomalies. Anomalies challenge models. Models are revised or replaced, and our picture of the universe becomes more detailed and more uncertain at the same time, because every answer raises new questions. Every mystery solved reveals deeper mysteries. The more we learn, the more we realize how much we don't know. Consider the observable universe. It's a sphere centered on us, with a radius of about 6.5 billion light years. Everything within this sphere is potentially observable, assuming our instruments are sensitive enough. Everything outside is not, because light from those regions hasn't had time to reach us yet. But this raises a question. Why is the observable universe the size it is? Why 6.5 billion light years, and not some other distance? The answer is related to the age of the universe and the speed of light. The universe is about 13.8 billion years old. Light has been traveling for 13.8 billion years, but space has been expanding during that time, so the objects that emitted the light we're seeing now are farther away than 13.8 billion light years. Accounting for expansion, they're about 6.5 billion light years away. This makes sense mathematically, but it creates a conceptual puzzle. The observable universe is finite because the universe has a finite age. But what about the total universe, the portion beyond our horizon? Is that finite or infinite? We don't know. It could be either. If the universe is finite, it has a total size, a total volume, a finite amount of matter and energy. but it might not have an edge, not in the way we normally think of edges. A sphere has an edge, a boundary where the surface ends, but a finite universe could be curved in a higher dimension, like the surface of a sphere, where you can travel in a straight line and eventually return to where you started without ever encountering an edge. Alternatively, the universe could be infinite. It could extend forever in all directions, with no boundary, no center, no edge. In this case, the Big Bang didn't happen at a point. It happened everywhere. Every point in infinite space was once compressed to infinite density, and then space expanded, separating those points. An infinite universe that's expanding is still infinite. Infinity stretched is still infinity, but the density decreases as space grows. Both scenarios are consistent with observations. The observable universe looks roughly the same in all directions. It's homogeneous and isotropic on large scales. This is consistent with both a finite, curved universe and an infinite, flat universe. We can't tell which is correct by looking at the observable portion alone. There are measurements that could, in principle, distinguish between these scenarios. The cosmic microwave background contains information about the curvature of space. If space is positively curved, like the surface of a sphere, the CMB would show a specific pattern of correlations. If space is negatively curved, like a saddle, it would show a different pattern. If space is flat, as an infinite universe could be, it would show yet another pattern. Current measurements suggest space is very close to flat. The curvature, if it exists, is extremely small. This is consistent with an infinite universe, but it doesn't prove it. The universe could be finite, but so large that the curvature is undetectable within the observable portion. Imagine standing on a planet with a radius of 1 trillion kilometers. The surface would seem flat to you, even though it's actually curved, because the radius of curvature is so much larger than the distances you can observe. So we don't know if the universe is finite or infinite. And if it's finite, we don't know how big it is. And if it's infinite, then the observable universe, vast as it is an infinitesimal fraction of the total. We're observing 0% of an infinite whole. This is a strange situation. We're trying to understand the universe, but we don't know if we're looking at a representative sample. The observable universe might be typical, or it might be anomalous. If the universe is infinite, there are regions beyond our horizon where conditions are different, where the distribution of matter is different, where perhaps even the effective laws of physics are different if the fundamental constants vary across space. Some theories suggest that what we call the universe might be just one region in a much larger structure called the multiverse. In inflationary cosmology, the rapid expansion that occurred in the first fraction of a second after the Big Bang might have been eternal in some regions, creating an infinite number of separate, causally disconnected regions, each with its own Big Bang, its own cosmic history. These regions would be forever beyond our observation, separated from us by regions of eternally inflating space. Other theories suggest that the fundamental constants of nature, the strength of gravity, the mass of the electron, the speed of light, might vary from region to region in the multiverse. Our universe has the values it does, and those values allow stars, planets, and life to exist. But other regions might have different values, leading to universes with very different properties. Most of these universes would be sterile, unable to support complexity or life. We exist in one of the rare regions where the constants happen to be right. This is the anthropic principle. We observe the universe we do, because we couldn't observe a different kind of universe. We wouldn't exist in those other universes to make observations. It's a controversial idea. Some physicists think it's a legitimate explanation for why the constants have the values they do. Others think it's giving up on finding a deeper explanation, a theory that predicts the constants rather than just accepting them as arbitrary. But whether the multiverse exists or not, whether the anthropic principle is valid or not, the core issue remains. We can only observe a limited portion of reality. Most of what exists, whether it's the unobservable portion of our universe or other universes in a multiverse, is beyond our reach. We're confined to our bubble of observation, trying to infer the nature of everything from the small sample we can access. And even within our observable universe, our observations are constrained by the nature of light and the structure of space-time. We see the past, not the present. We see ordinary matter, not dark matter. We see effects of dark energy, but not dark energy itself. We see the universe after recombination, but not before. We see what gravity and electromagnetism allow us to see, but not what might exist beyond those forces. The James Webb Space Telescope is pushing the boundaries of what we can observe. It's seeing farther, seeing fainter objects, seeing earlier epochs. But it's not overcoming the fundamental limits. It's working within them, extracting as much information as possible from the light that reaches us. And what that light is revealing is a universe that's more complex, more mysterious, and more humbling than we imagined. Those early galaxies, bright and massive and structured, are telling us that cosmic evolution in the first few 100 million years was rapid and violent. Stars formed quickly. Black holes grew rapidly. Galaxies assembled and began developing the features we see in mature galaxies billions of years later. The early universe was not a slow, gradual, smooth process. It was dynamic and chaotic. But why? What drove this rapid evolution? What provided the energy, the matter, the conditions that allowed structure to form so quickly? One possibility is that the density fluctuations in the early universe, the tiny variations in matter density that seeded structure formation, were larger than we thought. These fluctuations originated from quantum fluctuations during inflation, stretched to cosmic scales by the rapid expansion. If those initial fluctuations were slightly larger, then the regions that were slightly denser would have had stronger gravity, would have pulled in matter faster, would have formed stars and galaxies earlier. But if the initial fluctuations were larger, we should see evidence of that in the cosmic microwave background. The CMB shows us the density fluctuations at recombination, 380,000 years after the Big Bang. We can measure the amplitude of those fluctuations very precisely, and they're small, about 1 part in 100,000. If they were significantly larger, the CMB would look different. It doesn't. So either the fluctuations grew faster than we expected after recombination, or something else is going on. Another possibility is related to feedback processes. When stars form, they emit radiation. Massive stars emit intense ultraviolet radiation that ionizes surrounding gas. When stars explode as supernovae, they inject energy and momentum into the interstellar medium, heating gas and driving it out of galaxies. Black holes, when they accrete matter, release enormous amounts of energy, sometimes more energy than all the stars in a galaxy combined. This energy can heat gas, prevent it from cooling and forming stars, or drive powerful winds that expel gas from the galaxy entirely. These feedback processes regulate star formation. They prevent gas from collapsing too efficiently, which would turn all the gas into stars very quickly, leaving none for later. Feedback is crucial to understanding why galaxies have the properties they do. Too little feedback, and galaxies would be too massive, too full of stars. Too much feedback, and galaxies would be too small, unable to retain gas and form stars. In the early universe, feedback processes might have worked differently. The gas was pristine, composed only of hydrogen and helium, with no heavy elements yet. This affects how gas cools and how efficiently it can form stars. The first stars, forming from this pristine gas, would have been very massive and very bright, producing intense feedback, but the details are uncertain. It's possible that feedback in the early universe was less effective at regulating star formation than it is in later epochs. Perhaps gas could collapse and form stars more efficiently, leading to rapid bursts of star formation that made galaxies brighter and more massive than expected. Or perhaps feedback was more effective, but in ways we don't fully understand, leading to different patterns of star formation and galaxy growth. These are active areas of research. Astrophysicists are building detailed simulations of the early universe, trying to model the complex interplay of gravity, gas dynamics, star formation, and feedback. These simulations are computationally intensive, requiring supercomputers and sophisticated algorithms, and they're based on our current understanding of physics, which might be incomplete. The observations from Webb provide crucial tests for these simulations. If a simulation can reproduce the properties of the early galaxies Webb is seeing, their brightness, their mass, their structure, then it's probably capturing something important about the physics of that era. If it can't, then something is missing from the simulation, some process or parameter that needs adjustment. But simulations have limits. They can't include every physical process in full detail. They have to make approximations, focus on the most important effects, parameterize or ignore smaller scale processes, and they depend on initial conditions, the density fluctuations, the distribution of dark matter, the thermal state of the gas, that we infer from observations but don't know with perfect precision. So simulations are tools, not oracles. They can suggest explanations, make predictions, guide our thinking, but they can't tell us with certainty what happened in the early universe. Only observations can do that, and observations are limited by what light can reveal. There's a kind of circularity here. We use observations to build models. We use models to interpret observations. When observations don't match models, we don't know if the observations are wrong, the models are wrong, or our interpretation is wrong. We have to carefully check each possibility, ruling out instrumental errors, revisiting assumptions, considering alternative explanations. This is the scientific method, but applied to a domain where we can't perform experiments, where we have only one example, where much of the relevant information is inaccessible. It's a difficult, uncertain process. Progress is slow. Confidence in conclusions is provisional, and the possibility of being fundamentally wrong is always present. The early universe is especially challenging because it's so different from the present universe. The density was higher, the temperature was higher, the composition was simpler. Processes that are rare or weak now were common and strong then. Extrapolating our understanding backward in time is risky. The farther back we go, the more uncertain our models become. And yet, the early universe is crucial to understanding the present universe. The structures we see today, galaxies, clusters, the cosmic web, all originated from the seeds planted in the first moments after the Big Bang. The composition of matter, the ratio of protons to neutrons, the abundance of helium and other light elements, all were determined by nuclear reactions in the first few minutes. The patterns we see in the cosmic microwave background, the distribution of galaxies, the properties of dark matter, all trace back to conditions in the early universe. If we don't understand the early universe, we don't fully understand the present universe. The two are connected by an unbroken chain of causation. Every galaxy today is the descendant of proto-galaxies in the early universe. Every atom in your body was forged in stars that formed from gas enriched by earlier generations of stars, going back to the first stars that formed from the primordial hydrogen and helium. This is one of the profound insights of cosmology. We're connected to the early universe not just conceptually but materially. The atoms that make up your body, the carbon, oxygen, nitrogen, calcium, iron, were created in stars that lived and died billions of years ago. Those stars formed from gas that was part of galaxies that assembled in the first billion years after the Big Bang. The history of the cosmos is encoded in the matter that makes up our bodies, and the light we see from distant galaxies is the same light that was emitted when those galaxies were young, when the universe was young. That light has been traveling across space for billions of years, carrying information about conditions in the early universe. When we observe that light, when we analyze its spectrum, measure its redshift, determine its source, we're reading a message from the deep past. The James Webb Space Telescope is designed to read that message more clearly than ever before. And the message is strange. It's saying that the early universe was more active, more complex, more structured than we expected. It's saying our models need revision. It's saying we have more to learn. But it's also saying something else, something more subtle and more profound. It's saying that the universe is larger and older and more mysterious than our everyday experience can comprehend. It's saying that most of reality is hidden from us, either because it doesn't emit light, or because it's too far away, or because the information has been lost to cosmic expansion. It's saying that we're observers in a vast cosmos, seeing only a small fraction of what exists, trying to understand the whole from the parts we can access. And those parts are ghosts, images from the past, light that left its source billions of years ago, when the universe was younger, when stars were different, when galaxies were forming. We're not seeing the universe as it is. We're seeing its history, preserved in light, delivered to us across the expanding void. This is both humbling and isolating. Humbling because it reveals how small we are, how limited our perspective is, how much we don't know. Isolating because it reminds us that we're alone in our corner of space-time, separated from the rest of the universe by distances so vast that communication or travel is impossible, watching ancient light from regions we can never visit, learning about a past we can't change and a present we can't observe. The scale of the universe is terrifying not because it's large, but because it enforces limits on knowledge. There are things we cannot know, because the information doesn't exist here. There are regions of space we cannot visit, because expansion carries them away faster than we can travel. There are moments in cosmic history we cannot observe, because the light from those moments has already passed us, or hasn't arrived yet. We're living in a specific moment in cosmic time, in a specific location in cosmic space, with access to a specific subset of cosmic information, and that subset is small, perhaps infinitesimally small if the total universe is infinite. This is the context in which the discoveries from the James Webb Space Telescope should be understood. Yes, we're seeing early galaxies. Yes, we're learning about structure formation. Yes, we're refining our models. But we're also confronting the limits of what we can learn. Every distant galaxy we observe is a reminder that most galaxies are too far away to observe. Every mystery we encounter is a reminder that some mysteries might be unsolvable because the evidence is inaccessible. And this raises a philosophical question. If most of the universe is unobservable, if most of reality is hidden from us, does it matter? Should we care about regions of space we can never visit, events we can never witness, information we can never access? From a practical standpoint, perhaps not. The unobservable universe doesn't affect us. It doesn't interact with us. It doesn't pose any danger or offer any resource. It's irrelevant to our daily lives, to our survival, to our civilization's future. But from a philosophical standpoint, it matters profoundly. We're trying to understand reality, and reality includes the unobservable universe. The fact that we can't observe it doesn't make it less real. It just makes it unknowable. And that unknowability is itself a feature of reality that we have to grapple with. Science has always aimed at understanding the whole, the complete picture, the ultimate nature of reality. But cosmology is revealing that the complete picture might be forever inaccessible. We can understand our observable bubble, perhaps. We can map its history, measure its properties, explain its evolution. But the total reality, the entirety of existence, might extend far beyond what we can ever hope to observe or understand. This is a kind of cosmic agnosticism. Not agnosticism about whether the unobservable universe exists. We have good reason to think it does, based on our understanding of cosmology, but agnosticism about what it's like, what it contains, what its properties are. We can speculate. We can extrapolate from the observable portion and assume the unobservable is similar, but we can't know. And as time passes, as cosmic expansion continues, as more galaxies cross the event horizon, the unknowable portion grows. Information is being lost, not in the sense that it's being destroyed, but in the sense that it's becoming inaccessible to us. The universe we can observe is shrinking in information content, even as our instruments become more powerful. This creates a paradox. We're learning more, seeing farther, discovering new galaxies and phenomena, but the total amount of cosmic information accessible to us is decreasing. We're running faster to stay in place, gathering data while the universe hides more of itself from view. In the very long term, this process has an endpoint. If expansion continues, if dark energy remains constant or increases, then eventually all external galaxies will cross the event horizon. The cosmic microwave background will redshift into undetectability. The evidence of the Big Bang will fade. Future observers, if any exist, will live in an island universe, surrounded by darkness, with no way to learn about the larger cosmos that once was visible. This is sometimes called the cosmic dark age, not to be confused with the historical dark ages, or the cosmological dark ages between recombination and the first stars. This is a future dark age when the universe becomes observationally dark, when the evidence of cosmic history is erased by expansion. It's a disturbing scenario, not because it threatens us. It won't happen for trillions of years, long after the sun has died, long after the Milky Way has merged with Andromeda, long after any conceivable human civilization has either transcended, dispersed, or gone extinct. But because it suggests that knowledge is not cumulative in cosmology. There's a window of cosmic time during which certain observations are possible, and outside that window, the information is lost. We're living in that window. We can see the cosmic microwave background. We can observe distant galaxies. We can detect the expansion of space. We can infer the Big Bang. Future civilizations might not be able to do any of these things, and past observers, if there were any at earlier cosmic epochs, might have had access to information that we've lost, evidence of cosmic conditions or events that occurred before the observable universe reached its current state. This is speculative, of course. We don't know if there were observers before us. We don't know if information has already been lost, but the possibility exists, and it's a reminder that our perspective is limited not just in space, but in time. We're seeing a snapshot of cosmic history, the portion that's visible from our temporal location. Earlier or later observers would see different snapshots, different portions of the cosmic story. There's no complete, objective view of the universe. Every observer, every epoch, every location has a partial, subjective view limited by the speed of light, by cosmic expansion, by the properties of space-time. The universe as a whole might be knowable in principle if you could somehow step outside of it and see it all at once. But that's impossible. We're inside the universe. We're part of it. And that means our view is necessarily limited, necessarily incomplete. This is the ultimate message of the James Webb Space Telescope's discoveries. Not that the universe is large, we already knew that. Not that it's complex, we already knew that too. But that it's fundamentally inaccessible in most of its extent, and that the portion we can access is stranger and more puzzling than our models predicted. The early galaxies, too bright and too massive, are a reminder that we don't fully understand cosmic evolution. The expansion of space, driven by mysterious dark energy, is a reminder that we don't fully understand the forces shaping the cosmos. The dark matter, invisible and ubiquitous, is a reminder that we don't fully understand what the universe is made of. Every observation is a reminder of how much we don't know. Every discovery raises new questions. Every mystery solved reveals deeper mysteries. And all of this is happening against the background of a universe that's mostly hidden, mostly inaccessible, mostly unknowable. We can respond to this situation in different ways. We can focus on what we can learn, celebrating the progress we make, the mysteries we solve, the understanding we achieve. This is the optimistic response, and it's valid. We have learned an enormous amount about the universe. We've mapped cosmic history from fractions of a second after the Big Bang to the present. We've discovered planets around other stars. We've detected gravitational waves. We've imaged black holes. These are genuine achievements. Or we can focus on what we can't learn, on the limits of knowledge, on the vast extent of cosmic reality that will forever remain mysterious. This is the pessimistic response, and it's also valid. We don't know what 95% of the universe is made of. We don't know why the Big Bang happened. We don't know if the universe is finite or infinite. We don't know what lies beyond the cosmic horizon. These are profound unknowns. Both responses are honest. The universe is knowable and unknowable at the same time. We can learn about it, and we can recognize the limits of what we can learn. We can celebrate discovery, and we can acknowledge mystery. They're not contradictory, they're complementary. But there's a third response, and it's the one that cosmology increasingly points toward. It's the recognition that we're small, not small in a trivial sense. Yes, we're physically tiny compared to stars and galaxies, but that's obvious and uninteresting. Small in a deeper sense. Our perspective is small, our reach is small, our moment in cosmic time is small, our observable bubble is small, our knowledge is small. We're observers in a vast cosmos, seeing only a fraction of what exists, understanding only a portion of what we see, living for a brief moment in a universe that's existed for billions of years and will exist for trillions more. We're local, temporary, limited, and yet we observe, we think, we question. We build instruments like the James Webb Space Telescope and point them at the sky, gathering ancient light from distant galaxies, trying to understand where we came from and what we're part of. We know we're limited, but we push against those limits. We know most of reality is inaccessible, but we study the portion we can access. We know our models are incomplete, but we refine them, improve them, test them against new observations. This is the human response to cosmic scale, not to give up in the face of vastness and mystery, but to keep looking, keep questioning, keep trying to understand. Even if complete understanding is impossible, even if most of the universe is unknowable, even if our moment in cosmic time is brief and our perspective is constrained, the James Webb Space Telescope will continue observing. It will find more early galaxies. It will gather more data on how structure formed, how stars evolved, how black holes grew. It will refine our understanding of cosmic history, and it will encounter more mysteries, more anomalies, more phenomena that don't fit our models. Each discovery will expand our knowledge and reveal new unknowns. Each observation will show us more of the cosmos and remind us how much remains hidden. Each image will be a glimpse into the deep past, a message from the early universe, a ghost from billions of years ago. And we'll keep looking, because that's what we do. We're observers, questioners, seekers of understanding. We're small and limited and temporary, but we're here now with the ability to see across billions of light years, to look back billions of years in time, to glimpse the universe when it was young. That ability is precious. It won't last forever. In the far future, if expansion continues, the evidence will fade. The galaxies will disappear beyond the horizon. The cosmic microwave background will redshift into invisibility. The universe will go dark. But for now, in this moment, we can see. We can observe the ancient light from distant galaxies. We can measure the properties of the early universe. We can confront the mysteries of dark matter and dark energy. We can build telescopes and gather data and construct models and test them against observations. And in doing so, we encounter the terrifying scale of the universe. Not just its physical size, though that's immense. Not just its age, though that's vast. But its fundamental inaccessibility. The fact that most of what exists is hidden from us. The fact that observation shows us only the past, never the present. The fact that information is finite, bounded by horizons we can never cross. This is what makes the scale terrifying. Not that it's large, but that it enforces limits on knowledge, on exploration, on understanding. We can never know the whole. We can never visit most of the universe. We can never verify that our models apply beyond the observable portion. We're confined to our bubble, our moment, our limited perspective. And the early galaxies Webb is revealing, bright and massive and puzzling, are a reminder that even within our observable bubble, even within the portion we can see, mysteries remain. The universe is not yielding its secrets easily. Every answer comes with new questions. Every observation reveals new complexity. We're trying to understand something vastly larger and more complex than ourselves, using tools and methods that are necessarily limited. Operating within constraints imposed by the structure of space-time itself. It's an impossible task in some sense. We can never complete it. We can never achieve total understanding, but we can try. And in trying, we learn. Not everything, not even most things, but something. Some piece of the cosmic puzzle, some glimpse of how reality works, some fragment of truth preserved in ancient light, delivered across the void, captured by our instruments, analyzed by our methods, incorporated into our models. This is what the James Webb Space Telescope represents. Not a complete answer, but a better question. Not total knowledge, but deeper mystery. Not the end of exploration, but a new beginning, a new frontier, a new edge of the known beyond which the unknown stretches on, vast and dark and terrifying in its scale. And somewhere in that vastness, in regions we'll never see, in moments we'll never observe, in volumes of space beyond our cosmic horizon, the universe continues. Galaxies form and evolve. Stars are born and die. Black holes grow and merge. Structure emerges from chaos. And none of it is observable from here. None of it will ever be known to us. This is the universe we inhabit, mostly dark, mostly hidden, mostly unknowable. We see a small part, understand less, and recognize that even our understanding is provisional, based on assumptions we can't fully verify, extrapolated from a sample we can't prove is representative. And yet, we look up at the night sky, and we see stars, ancient light from distant sources, messages from the past, evidence of a cosmos that exists beyond our immediate surroundings. And we wonder, what else is out there? What else exists beyond what we can see? What would the universe look like if we could somehow transcend our limits, step outside our bubble, observe from a truly cosmic perspective? We can't do that. We're bound by the speed of light, by the expansion of space, by the fundamental structure of space-time. But we can imagine, and we can observe, and we can try to understand, knowing our understanding will always be incomplete, always be limited, always be haunted by the terrifying scale of what remains unknown. The James Webb Space Telescope has shown us galaxies from the dawn of cosmic time. It has revealed mysteries in the early universe. It has challenged our models and expanded our questions, but most importantly, it has reminded us where we stand, at the edge of a vast darkness, looking back through time, seeing ancient light from distant sources, trying to understand a universe that's mostly hidden from view. And in that darkness, in that vastness, in that unknowable expanse beyond our cosmic horizon, the universe continues, indifferent to our observations, our questions, our desire to understand. It simply is, and we are here, briefly, looking up, wondering, confronting the terrifying scale of everything we'll never know.